Hey everybody. So the way I want to go through the next step of the math is I want to start building the OpenGL transform that we use to implement our view frustum. Frustum. You know, I've been saying view frustrum for years. I was wrong. So sometimes I'll put frustrum in my notes because it's hard to unlearn something you've learned that's wrong. It's not a frustrum, like being frustrated, although it is frustrating. It's a frustum. Perspective. View frustum. Okay. Now, I'm going to make a big note here. For many people, okay, this is considered one of the hardest things that they learn, one of the hardest parts in computer science. Hard might be the wrong word, but confusing. So I'm going to break it down into parts, and I'm going to try to go quite slow and break it down for you, okay? So this is part 1, perspective. And we'll go through several parts to get through this. But if you find this confusing, go back and watch it, because this is really the fundamentals of how 3D works in a 3D gaming engine or a 3D movie engine. So you really want to know this. Okay, so we need a transformation, a transform, that's an F, matrix to implement our frustum, right? That's our goal. We want to go from some kind of world coordinates or in our other model from camera coordinates, but it's kind of the same thing, into our normalized device coordinates. So I want to go from -1 to -1, -1, -1. Okay? So the first problem we have, I'm going to draw out my eye here. This is my eye. And let's see if I can get this to go on the first try. So I have my view image plane here. Okay, this is my image plane. And then I'm going to draw out my lines. It's very important to make sound effects when you do this. Okay. And so you have our view frustum. View frustum, Jim. Not frustrum. There we go, I did it. Okay, so we have a view frustum here. I'm gonna start labeling these things, right? This is the top of my image plane. This is the bottom. This is my right. This is my left. And I draw my L's in cursive so you don't get mixed up with ones and things like that. This is my near plane, and this is my far plane, okay? So the first thing we want to do, let's just simplify our problem by assume that the eye is at the origin. Okay, so let's assume that the eye is origin and that it's looking into the scene. So I'm at the origin, I'm looking into the scene, right-handed coordinate system, I'm looking down the negative z-axis. Okay, that's the first thing we want to do. Luckily, we've already solved this. Right, we've already solved this with our camera transform. So we set up our camera so that we're in camera space. I'm looking down the z-axis. We've already solved this. So we already achieved this. Using the camera transform. So if you're not sure about that, go back and look at those videos, or just ignore it and say, yeah, let's just assume I'm at the origin looking at the z-axis, okay? And then when you move the camera around, if you're confused about how we can keep that assumption, then go back and watch that other video. So essentially, we are working in camera space. Good. Okay, we are working in camera space. So, how does it work? How do we do this, all of this conversion? Well, this is where things get a bit messy. I'm going to first draw this out. I'm going to draw this in a simplified fashion. I'm going to work on the y-axis first. So I'm going to just draw out cross section. Okay, this is my far, this is my near. I'm going to call it N for short. And this is my far. I'm going to call it F. Sure, why not? Okay. Now what I'm going to do is I'm going to highlight that if I have a point here in space called P, which has X world, Y world, and Z world coordinates, I'm going to highlight something here. Actually, I'm first going to draw in our axis. So this is our axis, our 0, 0 axis, okay? This Z axis, straight into the scene. This is what I wanted to highlight. If I draw a point from my eye, a line rather, if I can draw one straight, that would be nice. To my point, if I draw a line from my eye to P, I have two right triangles. And I can use the ratio of similar triangles to start making equations about this. And let's break that out again. Now I'm going. This is this bottom line I'm drawing here. I'm going to draw this out again. This line, this is my z-axis. This is the 0, 0. Okay, and then I have this here, this triangle, and I have this triangle. Now this is my point here, right? So this is my y coordinate in the world, right? That's that point right there. Now the height of this one is going to be my y on the screen, right? Because it's projected in. Now I also have this thing here. This is my z of my screen coordinate, which just happens to be my near plane distance, right? We already have that. Near is how far away from the camera it is. I already have that. And this point here is going to be my z in my world coordinates, which we also already have because I have a point in the world. I have x, y, and z in the world, so I know zw, I know zs, and I know the y coordinate here, so I can solve that one. And this is how we do it. So the y in screen space over y in world space, so this edge, the ratio of those edges equals the ratio of my, z in my screen space over my z in my world space, right? So it's the ratio of similar triangles. Those are the same ratios. And I can just, I know this here is really just n. And I can just say equals to n over zw. Now, based on what we're saying earlier, I'm going to put a negative in front of my zw. Let's just start from positive z values. Okay, right-handed system. Let's just start from positive z values from the previous lecture. So yeah, since we're looking to the z-axis negative, let's just make it positive so we're working in positive z numbers. Great. So I can calculate the height, this ys here, using this law of similar triangles, and I can rearrange this formula so that I get y on my screen is just going to be the distance to the near plane times y in the world coordinate divided by negative z in the world coordinate. So this is basically what we saw in the previous lecture, except now we showed how it works with similar triangles, and we have that new parameter n in here, where we can control how far away that plane is. And it turns out that it goes exactly the same for s. X screen parameter is n times x in the world over minus z in the world. And remember that minus, that's just to keep things positive. The math just because if we were in a left-handed system, it wouldn't be needed. It's just because we're in a right-handed system, z is negative, negative gets weird. We want to keep everything positive. So that's it. So if I use my near plane in my equation, it turns into just a multiplication. I just multiply first by the near distance, and I've proven that with the law of similar triangles. So the next question is, how on earth do I turn this into a matrix? So how to turn this into transform. matrix. Well, we've already figured out this divide by z business, but let's work on the rest of it. So first of all, we have x in the world, y in the world, z in the world 1. And then all I'm going to do is, it's actually quite simple. I'll put an n. We look at this and go, all right, I need n times, for y it needs to be n times y. For x, we need the n times x. So we just put that right into our matrix. So for x, it's n 0, 0, 0. It's going to be nxw. That's it. For y, we do the same thing. N times yw. Let's leave z for now. Okay, we'll figure that out later. And then for the y w coordinate, we already do what we've learned. And so the y w coordinate is going to be negative zw. This actually should be a 0. Negative zw, so we don't add that 1 in there. All right. And then we know that then this equals n over n times xw over minus zw, n times yw over minus zw. We'll leave z for now, and then this is going to be 1. Perfect. So we've now shown how we can start to model this frustum and start to turn pieces of this frustum. Right now, the near coordinate, the near plane, we can turn that into our pieces of our transformation matrix. We can just multiply that in, and we can solve for that part of the equation. Now, this handles our perspective quite nicely. Okay, this handles our perspective. But we need more than that. If we're going to go to normalized device coordinates, we also have got to go to -1 to 1. We also have to transform from -1 to 1. So that's kind of like what we did for orthographic. Okay, so it's very similar, but the math turns out to be different because we have this multiplication for near and far and this division that changes things a little bit. So it's very similar to the orthographic. Okay. All right. I'm just thinking in the back of my head here. I think I'm going to zoom up. I think I made this mistake here in the previous slide set as well. Yeah, looks good. Okay. Fine, I didn't. Good news. Okay. All right. Well, we'll stop here and we'll come back and we'll learn about how to set up that scaling part of our frustum calculation.